Hello, everybody. This is Tom Rue. I'm from Chelsea Communications, and today I'm going to be serving as your moderator for today's SNIA Networking Storage Forum webinar, namely, what NVMe TCP means for network storage. I would like to welcome and thank our great guest speakers for today's talk, J Metz from Cisco and Sagi Grimberg from Lightbits. I think everyone will agree that NVMe and subsequently NVMe over Fabrics have taken the industry by storm over the past couple of years. And now that the NVMe TCP specification has recently been ratified and it becomes the newest kid on the block, it's causing quite a stir. And given the number of people who have pre-registered for this webinar, I believe that that is the case. So before we get moving on this, we have a lot of information to go over, so I'd like to just get through some of the logistics. One thing to be aware of, if you happen to have a lot of windows open in your browser and you find that the audio in your webinar is choppy or difficult to listen to, we have found that clearing out your cache might be useful in fixing this problem. Also, if you might have the opportunity, you'll have the opportunity to rewatch this presentation on the BrightTalk site, as well as download the slides. During the presentation, we will attempt to answer questions as we can. Questions can be asked by pressing the question button at the bottom of your BrightTalk browser. In addition, we hope to have some time left at the end of the webinar for you to ask some questions. However, if there are some questions that don't get answered, you'll be able to refer to them and get answers from them in the Q&A blog that will be typically available within 1 to 2 weeks after this webinar. Presentation is vendor neutral and brought to you by SNIA, the Storage Network Industry Association. That being said, there is some legal stuff that I need to go through. All material in this presentation is copyrighted by SNIA unless noted. You can use any of the material in this presentation, but you are not allowed to change any of the files. To keep the lawyers happy, no warranties expressed or implied. In other words, use at your own risk. Now that I've gone through some of the introduction, let's talk about NVMe TCP. Here is our agenda for the webinar, and for now, I'll turn the program over to Jay. Hello, Jay.
Hey, Tom. How you doing?
I'm well.
Great to hear about that, and hopefully I can be heard pretty well over the system. Yeah, thanks. Yeah, we've got a lot of interest in NVMe over TCP, and I'm extremely happy to be able to join the stage with Sagi Grimberg, who is the lead author of this for the NVMe specification. So I know that most people are probably dying to hear about him, but I am going to tease everybody a little bit longer and give a little bit of an NVMe over Fabrics primer to help bring people up to speed so that Sagi's section is actually going to be placed in the larger context. But nevertheless, for our purposes here, we're going to assume that you already understand the basics of NVMe. Unfortunately, this is the time constraint that we have to play with. So if you're unfamiliar with NVMe, you may want to watch some of the earlier presentations on NVMe basics, even the NVMe over Fabrics basics that SNIA has put together, as well as the NVM Express organization. However, for today, we thought it would be a good idea to go back into a short primer of NVMe over Fabrics, just to level set. And then we're going to be talking about, of course, what you're here for, the NVMe over TCP itself. And we're also going to be talking a bit about what makes a storage network good, as opposed to just a storage network. And then we'll be discussing some of the different approaches to how storage and networking intersect. Now, to that end, we won't be discussing RoCE, iWarp, or Fiber Channel NVMe over Fabrics, and we won't be discussing InfiniBand, simply due to time constraints and the fact that it's not the point of the webinar. There are other webinars that cover those in greater detail, and some of the links to those presentations will be provided at the end of today's session. So at the very end, we're going to be bringing everything back together and circling back to what constitutes good storage networking philosophy as it applies to NVMe over TCP. Now, having said that, let's start a little bit with understanding some of the important bits about NVMe over Fabrics in general, and understanding these parts will go a long way to understanding the TCP portion of the specification. Okay, so at a high level, and as we record this presentation, there are now 3 official transport methods for NVMe over fabrics. The latest one, TCP, was ratified by the Board of Directors of NVM Express in November of 2018, so it's the newest kid on the block. But it's important to note that the main goal of NVMe over fabrics, or fabrics as it's typically shortened down to, is to maintain the same multi-queue model across the network that you find with NVMe in a PCIe environment. Now, the idea here is to provide a great deal of parallelism and low latency capabilities, and as a result, one of the key features that you can independently scale the storage and compute to maximize the resource usage for specific workload requirements. Okay, so having said that, what's so special about NVMe over fabrics? Well, as I said, we're not going to go over too much of the basics about NVMe, but it is important to note that NVMe works on the basis of queue pairs. There is an admin queue, which is used for the controller management, and I/O queues, which are used for, you guessed it, I/O. And so these queues can be very deep, up to 64,000 queues and up to 64,000 commands per queue. In reality, you're not going to see a lot of these queues put into practice because they're still memory bound, so it still takes a lot of memory to have that kind of queuing in a single system. But as far as a model is concerned, it winds up being consistent across the board. So we have this multi-queue model for NVMe that we want to maintain across the transport networks. And so we want to keep these as ubiquitous as possible, regardless of which transport we're using. And that way we can extend the efficiencies across whatever fabric we choose. Now, one of the interesting things to keep in mind is that when you start to look at what happens when you scale, you can remember that we attach a queue pair to a CPU core and then connect to an NVMe controller. Now, one of the cool things about NVMe over fabrics is that we can do this to multiple systems as well. So it's useful to know that an NVM subsystem does not have to mean an appliance or an array. It could mean a device that has multiple subsystems or a logical set of constructs that are located in a distributed fashion across the network. Either way, we're using each controller to provide its own separate set of queues instead of where we would use a single set of queues for multiple controllers like we would in some of the more traditional systems. That way we can actually maintain a lot of the efficiency regardless of how big the systems actually wind up getting. Now, hang on a second. I'm afraid I have a lingering cough and I have to hit the mute button every once in a while. Okay, so this is where the magic of fabrics actually resides in the specification. What makes NVMe over fabrics is something called bindings. So an NVMe over fabrics connection is part of the specification when and if it uses the proper bindings between the NVMe layer and the transport layer. Now, the reason for this is because different transports have different requirements, and we're going to see that a little bit later on. A transport may require a separate connection for each admin or I/O queue, or it could be the same connection for all admin and I/O queues associated with a particular controller. In other words, these bindings are the glue that links all of the NVMe bits to the transport bits. Now, this is not to say that you don't have the ability to have NVMe placed on a network without using these bindings, all right? It's just that if you're going to be using something that's officially considered a binding, or rather officially considered an NVMe over fabrics as part of the specification, this is how you can tell the difference. There's nothing wrong with doing your own thing. There's a lot of proprietary ways of doing this that are available out in the marketplace right now. But this is what makes an official NVMe over fabrics compliant specification. So this is where we start to get to some of the nitties and the gritties. Now, what we're seeing here is a basic generic model of how the NVMe host driver gets commands to and from a remote NVMe controller on a storage target. Now, the process is pretty straightforward. Now, in this particular case, and this is true for all the different fabric types, what we do is we take a host driver and we encapsulate a submission queue entry into a NVMe over fabrics command capsule. And if you're familiar with NVMe, you'll know what I mean when I say a submission queue entry in a submission queue. And so what we want to do is we take that, the network transport then takes that capsule and sends it across the wire, at which point in time it's got its grubby little hands, and it sends the capsule to the NVMe controller, which then decapsulates it into the NVMe submission queue. Once it's in the submission queue of the NVMe controller, the controller processes the command, and when it's done, it encapsulates the completion queue into a response capsule, and then sends that capsule to the NVMe over Fabrics queue, and once again, the transport sends the capsule back across the network, where it's then decapsulated and eventually gets put into the completion queue. The host driver is then going to process that completion queue entry, updates the submission queue pointer, and the process happens all over again. And the cycle begins again. It's a circle of life for NVMe. So, what this means, though, is that the key differences that you have to keep in mind has to do with what happens on those transport models. So from here we start to head down the rabbit hole, and we're going to be getting into some pretty specific and nuanced aspects of the differences of NVMe over Fabrics transports, with particular focus on TCP, of course. Now, once again, we're back to the fundamental point about NVMe. We're going to be using storage in terms of memory semantics. In other words, we're going to be basically treating the end device as a memory device. It's a storage device that has the same kind of memory semantics, and that's why we can actually use PCIe and the remote fabrics in a similar kind of fashion. However, there are still some differences. So when we use PCIe, for instance, we're going to be using a memory mapped model, and the commands and the responses, as well as the data, are going to use shared memory. Now, when we want to move outside of a server, though, the propeller spins the other way. So we can extend that memory semantic remotely using either remote direct memory access, by which means the data is transmitted, can be done using capsules or shared memory, and we're going to get to that in a second. Or we can use, we can pass the data back and forth using messages themselves. And as a result, we need to be able to have NVMe communicate with those types of transports natively. And in this way, both Fiber Channel and TCP share similar characteristics about how they handle that command data transfer, more so than Rocky, iWarp, and InfiniBand, even though for some of those, Ethernet may be the common underlying transport mechanism. So let's take a look at what that actually looks like. Now, remember that there are two different ways for these capsules to be sent for the command data. And just because we may be using Ethernet, it doesn't mean that they're all going to work in exactly the same way. And this is what I mean. So what we're talking about here is that in this graphic, and you'll see that in the next one, you'll see the relationship between the command sent and the data sent, and they can differ. So in the case of PCIe or RDMA transports, the method by which the commands and the data are sent is separate. In particular, when NVMe needs to send commands and response capsules, they're sent using messages. So the commands are sent using the messages, but the actual data itself is transferred using those memory semantics. And that is, when the NVMe controller on the target is processing the data, it uses the normal data transfer mechanism inherent to that transport type. So, for example, with RDMA, you process a read-or-write with the appropriate RDMA read-or-write mechanisms. In fact, SNIA has a presentation specifically dedicated to how RDMA and NVMe work together. So, however, the other way of doing it, in contrast, is to use messages for everything. And now in this situation, both of the commands that are sent and the data that is sent use messaging between the host and the target's NVMe controller. So both Fiber Channel and TCP use this mechanism. So in this way, there's a lot more similarity between the two protocols for for Fiber Channel and for TCP than with the memory-based semantics, despite the fact that both TCP and RDMA solutions like Rocky and iWarp all use Ethernet. So just because something is on Ethernet doesn't mean it's all treated exactly the same way, which can have profound implications for network architectures. That distinction can be pretty profound, and especially when we start talking about network design, which we'll get to a little bit later. One of the things to keep in mind, though, is that when it comes to the overall system performance, those arrows that you see on these graphics and the one before, they represent the networks. And what happens in the networks and in these arrows are very important. And as Sagi talks to NVMe over TCP, keep in mind that the way that the actual mechanics of NVMe over TCP work means you have to think about the overall big picture of a network, a storage network in particular. Having said that, I will pass it off to Sagi to introduce NVMe over TCP for us.
All right, thanks, Jay. Was a very good summary. So in this section, we're going to go cover what NVMe over TCP is really in a high level. So to start off with some motivation about why NVMe TCP is a good idea. First and foremost, it's ubiquitous. It basically runs on everything and everywhere, as long as it's Ethernet, of course. It's very common and well understood. In fact, even basic networking skills require knowing TCP front to back, actually. TCP delivers very good performance and performance scaling once you go into multi-threaded applications. It's very well suited for large-scale deployments and longer distances. And TCP is evolving. It's actively developed, both from the standard side and from the software and hardware implementations of the various components in the network. And lastly, NVMe TCP supports in-transit encryption with TLS, which is becoming increasingly important. But also, you need to watch out for a few things. When you choose NVMe over TCP, you would want to make sure that your network infrastructure may be well designed to meet your latency and performance requirements. Not paying attention to that may make you miss your targets. And also, some applications have very strict performance thresholds, which an unoptimized TCP stack or TCP implementations may fall short of. Now, one important thing to understand is that NVMe over Fabrics capsules and NVMe TCP PDUs are different things, actually. A Fabrics capsule, as Jay mentioned, basically represents NVMe commands and NVMe completions, or Fabric-specific commands. In practice, command capsules look like NVMe commands with some form of SGLs and optionally in-capsule data. And response capsules are actually no more than NVMe completions usually. Well, NVMe TCP PDUs really encapsulates every protocol message that undergoes the wire. That can include Fabrics capsules, data payloads, ready-to-transfer messages, connection initialization, and termination messages. As we'll see a little later, in the most generic form, a PDU will include a header, digests, padding, and data. So here we're covering a bit about how Fabrics capsules map to NVMe TCP PDUs and how these are laid out on top of TCP segments. So in this example, we have a Fabrics capsule with encapsulated data that maps usually one-to-one, or always actually, one-to-one as a PDU payload. That payload is prepended with a PDU header, and this basically constructs an NVMe TCP PDU. Now that PDU is spanned across multiple TCP segments, where each segment is of size of a maximum segment size in TCP. Additionally, we have, in this example, we have two Fabrics capsules with no encapsulated data, which again map as two different PDU payloads, which each prepended with a PDU header. Now, in this case, both NVMe TCP PDUs coalesce into the same TCP segment. So you can have it, when you open a trace, you can find it in either way. Now, what's a PDU and how does it look like? So, in fact, it's an encapsulation of every payload that is transferred across the wire. Starting from the header, every PDU has a header, which consists of an 8-byte common header and a type-specific PDU header addition. Now that header is optionally protected with a header digest integrity checksum that protects the integrity of the header itself. After that come optional pad bytes for some enhancement for implementation-specific alignment constraints. And after that, we have the data, should it exist in the PDU. And that data can optionally also be protected with its own data digest integrity checksum. Now, this slide illustrates basically in high level the differences in the encapsulation process of the different NVMe transports. So every NVMe command starts basically as an NVMe submission queue entry and some transport agnostic buffer handle. On the bottom arrow for PCIe, that buffer handle is basically represented with a PRP or an SGL, and that submission queue entry is posted on NVMe submission queue, as we saw earlier. For fabrics on the right hand, the buffer handle is always an SGL, and basically a fabrics capsule is formed to represent that NVMe command. Now, for that SGL is of course transport specific. When you look at NVMe over RDMA, that SGL become a keyed SGL, which is represented with an RDMA R key. And this capsule as a whole is posted on an RDMA queue pair as a send message and then being sent to the remote side. If you look at NVMe TCP, then we have a PDU header that's prepended to the NVMe over fabrics capsule. And we use the transport SGL, which basically say that all the addressing is relative to the I/O transfer. And both sides, both the host and the controller, are responsible for scattering and gathering memory to the individual sides. That PDU is sent down the TCP/IP stream channel. Similarly, if you look at fiber channel, an FCP NVMe header is prepended to the capsule, and the same transport SGL is used. And basically, that message is sent down the fiber channel network, and basically starts a fiber channel exchange, which we won't cover here. Now, this sort of giving a high-level overview what the command processing looks like on both ends. It can be viewed logically in three different layers. One is the fabrics or NVMe layer. Below that we have NVMe over TCP and what works there. And below that we have the TCP/IP stream. Now, basically a host, everything starts when a host submits an NVMe command on the transport submission queue. So every transport will usually have some sort of transport submission queue that is the interface to the host for issuing I/O commands. Now that queue, that submission queue, is processed by what is often called an NVMe TCP reactor context, which is essentially a context that's invoked by outside events like host submissions or data coming from the network. So a host would issue an NVMe over fabric submission queue entry. At that point, the reactor would fetch that command, will build a NVMe TCP PDU, and will send it down the TCP/IP byte stream to the remote side. Now, on the remote end, we'll usually see something similar which is of course implementation specific, but in high level we'll see something similar. The NVMe TCP PDU will reach the controller side, will be processed by the NVMe TCP context, which will decapsulate the NVMe over fabrics capsule, or basically an NVMe command, and will move it back to a back-end processing stage, namely posting it to the remote submission queue of the NVMe controller. Now, once the controller finishes with the I/O, it will generate a completion queue entry, which would again be processed by NVMe TCP. A completion capsule, response capsule will be built, and that will be, and the NVMe TCP context will build an NVMe TCP response capsule PDU. and then we'll send it down the same byte stream in the opposite direction, as the TCP streams are bidirectional. And it will then reach the host. The host will the host NVMe TCP reactor context will be invoked from the data coming from the network, will decapsulate the fabric's capsule, and generate a local NVMe completion. Now, expanding the view into a controller-wide association, basically we have the controller association consists of multiple queues, as in we see usually in NVMe. First one is the admin queue, and then a set of I/O queues. Now, by design, every NVMe queue and NVMe over Fabrics queue is mapped one-to-one to its own NVMe TCP connection and TCP byte stream. Now, the fact that NVMe queues are completely independent, that means that also for NVMe over TCP or TCP, we don't have any controller-wide sequencing or serialization. And also on the controller side, we don't have any reassembly constraints on out-of-order data that comes from different queues. Now, the one positive thing to understand is that we obviously don't have shared state across NVMe queues, hence on top of NVMe TCP connections, which are accessed in the hot path, which brings a lot of efficiency benefits. And also, usually as you find in NVMe, each NVMe queue and its backing NVMe TCP connection will be assigned and accessed by different CPU cores, which again gives you very good performance scaling once you go multi-threaded. Now, one last thing to note about how the controller association is formed is, like other fabrics, when an NVMe TCP connection is formed, it's kind of floating and unbound to a specific controller. The actual binding happens when the Fabrics Connect comes, right after we establish the NVMe TCP connection. That NVMe over Fabrics Connect capsule contains the controller ID, and at that point on the controller side, that NVMe TCP connection is formed associated with an NVMe queue, which is also in turn associated with a controller instance. Now, if you look at the I/O flow in high level of NVMe over TCP, it follows the classic RPC models that you will see most storage protocols use. On the left-hand side, you have the read I/O flow, and on the right-hand side, you have the write I/O flow. So on looking at the read I/O flow, it all starts when the host issues a command capsule PDU, which is again a Fabrics capsule encapsulated in a specific PDU type, which basically is a command capsule. It's issued from the host to the controller. The controller will answer by issuing a series of controller the host data PDUs, which basically are split up to however the controller wants to split them up. And then it will pipeline a response capsule PDU to complete the I/O to the host. Now, since TCP guarantees us in-order delivery, you don't need to wait for the data to complete before you actually issue the response capsule, which is again good for efficiency. On the right-hand side, you have write I/O, and which again starts in a command capsule PDU, where you want to write data to the controller. That command capsule PDU can optionally have encapsulated data, but for this example, it doesn't. And in response, the controller will send an R2T, or ready to transfer PDU, with a given length. The host in response will send a series of host-to-controller data PDUs, again, host-to-controller noting the direction of the data PDU, back to the controller, and the process will iteratively rewind and happen until the entire I/O data transfer is completed. And the controller will then issue a response capsule PDU to terminate, or let's basically complete the I/O on the host side. Okay, so it's also important to note some of the potential issues or concern when you actually go ahead and choose NVMe TCP. First concern that comes up a lot is that absolute latency is higher than RDMA. Well, in general, that could be the case, usually by several microseconds, and it's really dependent on the workload that you're actually running and the implementation that you're actually using. However, it only matters if the application is that sensitive to the sort of latency differences. So if you have a very strict latency guarantees in a very controlled environment, then you have various different options. As for head-of-line blocking, usually head-of-line blocking will generate higher latencies. However, NVMe TCP protocol basically says that a controller will and can break up large transfers into smaller pieces, which basically give a chance to smaller IOs get in between. And also, the host can issue, large bulk writes and small reads on different queues, which is usually often a lot of the cases. And that actually completely omits the problem. And also NVMe priority-based queue arbitration also helps to completely isolate small reads versus large bulk writes. Now, could Incast be an issue? So Incast is a common problem or concern for TCP/IP. However, note that a lot of attention is being put on this area specifically both from the standard side and from software and hardware components all over the network. In terms of hardware acceleration, NVMe TCP is designed to be very extremely efficient running in software on host CPUs. Nevertheless, offload devices are coming to market as well. Now, at this point, I'm going to give it back to Jay to talk about some of the network aspects that are apparent when you use TCP.
Okay, Sagi, before we go to Jay, we've had several questions come in, and since we're doing pretty well on time, I was going to ask a couple of those. First of which is a very simple question that I neglected to answer earlier, is that can we get the slide deck for review? And yes, of course, the deck will be available very shortly, and I'll post that to the to this presentation in a few minutes. Let's just go through a couple of these questions. I don't know if we're going to be able to get through them all because there are quite a few. First one, who is responsible for updating the NVMe host driver? Jay or Sagi, you want to handle that one?
I can take that one. In terms of who is responsible, that depends on which driver we're talking about. Upstream driver exists and are contributed to the Linux kernel and also to the SPDK environment. Both of these projects have a very well and healthy community that are very responsive and in adopting and enhancing the stack and the implementation itself. And we also have OS vendors and interested parties that are also contributing. Now, also different OS vendors that are outside of what I just mentioned will also be responsible, I guess, to basically support and maintain their individual drivers.
There's a question here, can we show some NVMe TCP specific commands?
Well,
would we rather hold that for the blog?
So we don't have specific illustration about how the command look like. We do have a generic illustration about how a PDU looks like and what are the different sections that it has, and we went over those. And basically every protocol message looks like that PDU in the most generic form.
Excellent. Thank you.
Yeah, that goes back to the bindings part of it, right? So to that point, the question really needs to be broken down into what constitutes an NVMe command versus what constitutes the intersection between the transport and the NVMe layer, which is the PDUs that Sagi was talking about. But there's no specific NVMe over TCP commands per se.
Okay. Thank you, guys. One more. Why NVMe CQ is the controller and not on the host?
JD, you want to take that, or should I?
Yeah, sure. I mean, the NVMe completion queue is on the host, but the actual this goes back to the part where we broke down the generic transport mechanism. So when a completion queue entry is encapsulated, that would be on the responsibility of the NVMe controller to encapsulate that entry into the NVMe over Fabric's capsule. And then that entry is then sent by the capsule, or sent by the transport in a capsule to the host, where it is then decapsulated by the completion queue. So the completion queue is always on the host itself.
Okay. I think we'll do one more, and then maybe we'll hold the rest until the question and answer period, so that Jay can get through his last portion. So this one. So the send queue and the completion queue run asynchronously from each other with variable ordering, depending on the I/O latency of a request. Is that
mostly correct? Right. But not depending upon the latency. So the way that NVMe is designed is that the NVMe controller can process any command in any order that it wishes. You do not need to have in-order processing of commands inside of NVMe. There are some rare exceptions which involved something called fused commands, but they're actually quite rare. But the submission queue really is a buffer for being able to have an outstanding set of entries that the NVMe controller can then process according to its own needs. And then the completion queue is, of course, completely independent from the submission queue, with one singular exception. There is a submission queue pointer that indicates where the sequence of a command actually exists, and then the completion queue, when an entry is processed, will update that submission queue pointer to free up the memory resources in the submission queue. Outside of that, they act independently from one another. Sagi, did you have anything you wanted to add to that?
Yeah, so that was a very good point. So the controller is has the level of freedom to process commands out of order. However, it's important to note that some transports have strict ordering in terms of the command delivery ordering, that it needs to be in the same order of the ones that are issued by the host. And some also can reorder commands on the HBA level or on the network side.
Okay.
Right.
Thank you. I'm going to get us going back onto the last piece of the presentation so that we can stay relatively on time, and we'll see if we can answer a few more of these questions at the end. So Jay, take it away.
Yeah, I'm looking through some of these questions myself, and I can see where you have our work cut out for us on this Q&A blog, that's for sure.
Are you kidding?
But they're excellent questions, and they're really good. So I'm going to try and see if I can try to address some of the concerns that are coming up in the next section, because there's a lot of stuff in here that we will be covering. So one of the things that's really important to note is that the NVMe protocol, and NVMe over TCP in particular, can have profound impacts on the network design. We're making things efficient in this with all the parallelism that we've got, but the independence of the NVMe controller and the host driver, and the queues can act independently of one another, and they can actually have a lot of freedom, as Sagi mentioned. All of these efficiencies will and can alter the performance characteristics of a network. And so remember back when I was showing you the arrows about how the command data is passed and how the data is passed and that sort of thing. Those arrows are really representative of the networks. And so it's important to note how the key aspects of TCP in this particular case could wind up being important, since that is the foundation for how the networks communicate. So one of the things that we're going to note is that we're going to talk about a couple things here. There's a lot of nuances that go far beyond our time limit, and we can't go into all of the advances in TCP. We're not recommending any particular solution. Rather, we're just trying to point out that there's more to think about this than just, hey, I'm using TCP, it's all good, and all my problems are solved, and I've just cured world hunger because I'm using TCP. It's not quite that simple. So one of the things you have to realize, and one of the things that's important to note, especially when it comes to storage networks, is that we really want to design a network based upon what the application requires. In storage networks, which we're really talking about here, we're talking about TCP, but effectively we're talking about storage networks, you really shouldn't be designing a network that has a lot of buffering. And the reason why this is because when you add buffering into a network, you're going to add in latency. That's what a buffer does. It basically creates a staging area for sending information across the wire. Now, buffering for that reason in a storage network is an undesirable condition, and you need to treat it with great care. So when we talk about networking characteristics of storage environments, whether they're in the context of fiber channel or Ethernet, it doesn't matter what the protocol is, but rather it really matters what the application I/O requirements are. And this goes back to what Sagi was talking about in terms of the caveats about NVMe over TCP. Adding additional latency really becomes something of an issue if the application cares about it. Some do, some don't. So, in other words, the application is king, and we must all hail the king. Mismatching an application with an incorrect networking configuration is a recipe for a really, really bad day. So, to that end, not all TCP stacks are created equal. So when I usually talk about TCP-based storage with people, the conversation rarely goes further than the fact that we're talking about TCP. However, there are several different flavors of TCP, and they're not all created equal. The most common stacks rely on drops. That's what everybody knows about TCP. And it's true that they require proper network buffering to handle or avoid all these excessive drops. So newer TCP stacks that look at round-trip times or other feedback loops to monitor the throughput are optimizing for smaller or even zero buffer networks. And this underscores the need for accurate round-trip time estimators. So it helps to know which stacks you're using. As you can see, there are many, many different stacks, and some of the newer ones that can provide a profound impact on the storage networks in particular. Now, perhaps someday we'll be able to do a webinar on how these different stacks compare for storage traffic. I suppose we'll see. For right now, just keep in mind that when we say TCP, it's not this monolithic entity that just you throw onto a network and all of a sudden your storage network works really well. Now, as we know, TCP flows have a tendency to grab as much bandwidth as possible. That's how TCP works. And NVMe over TCP adds the additional greediness of never blocking on an I/O, unlike some other TCP implementations. So every send into the wire is effectively with the message, don't wait. And we rely on that connection to pick up wherever we leave off when congestion hits. Now this allows us to first multiplex between connections on the same thread, and also never to block or never schedule to sleep. Now, this has a rather aggressive impact on the network. And as a network TCP reacts to that aggression by dropping and retransmitting a signal for network congestion, TCP will need that retransmission in order to handle the congestion control. So this is basically the give and take, right? We want to be able to give as much bandwidth as possible and then back off wherever. And TCP typically tends to do this by dropping, and that's where we get this familiar sawtooth pattern. So we wind up finding ourselves in something of a catch-22 paradox here. The buffer question becomes something of a Goldilocks situation. On the one hand, if you don't have enough buffer, you're going to have poor utilization of the link bandwidth. And if you have too much buffer, you're going to increase the latency. So as you know, NVMe over fabrics is highly latency sensitive. So obviously, simply throwing more buffer at the problem going to have some adverse side effects on your storage performance. More buffers equals, more latency. So let's define a few terms here, and namely the difference between buffer and buffer occupancy. There's a little bit of a side trip into the networking world here. A buffer is a physical memory allocation, and it might be for a specific queue, or it could be shared among a number of them. The size of the buffer is the ultimate limit. You can't store a message if you've got no place to put it. The occupancy of a buffer is how much of it you're using. So let's say you have a street, and the street is empty, and that street has a certain amount of capacity. But if the street is empty versus the street is half full or the street is full, then the occupancy is different. Same thing with your wire on the network. And we certainly want a buffer to be deep enough to perform a shock absorber function, right? So we want the buffer occupancy to be as statistically shallow as we can get because of that impact on latency. So because we want to minimize the latency, especially for NVMe traffic, simply having a deep buffer with no mechanism to manage the occupancy has the effect of maximizing latency, and this is bad. So the trick is to have just enough buffer to get the best possible link utilization and latency. All right, so there's our buffer tutorial here. But the thing is that even normal TCP traffic is greedy, and it's going to cause the length of a bottleneck queue to grow until the packets are dropped, and we're back to that familiar Sawtooth patterning once again. So when we have the large flows that go across the same queue as shorter flows, also called elephant and mice flows in the common vernacular, two problems occur. First, packet loss on the short flows can cause Incast problems, which we'll get to in a moment. And second, even if there's no lost packets, the short flows can experience increased latency as they're in the queue behind packets from the large flows. In other words, large elephant flows can hog the wire by blasting and starving the poor little itty-bitty mice flows. So there are two methods of solving this problem. The first is to increase the buffer size in the switches, which we just talked about. And the second is to be more proactive and tell the sender to slow down before the packets get dropped. So this can lead up to something that up until recently has been rare. It's getting more and more common as the traffic across networks has been increased. And that's something called TCP Incast, or also called TCP Incast collapse. TCP Incast happens when synchronized sessions arrive at a common congestion point at the same time. So each TCP session is going to grow the window until it detects congestion, which then triggers packet loss. At that time, all TCP sessions back off at the same time. And as I said, up until recently, this has been something of a specialized case of network traffic. And it requires every flow to arrive at exactly the same time. You may remember that Sagi was talking about the increase in the number of queue pairs, and each one takes up its own TCP session. So in this example, then, you can imagine these red arrows that we just had in the last graphic as potential NVMe over TCP sessions, each with their own queue pair and each going to the same destination. So in this example, then, it's conceivable that an NVMe device could be receiving messages from a source which could wind up creating a buffer overflow situation, at which point in time all of the sessions will back off. Now, as we've also seen, we designed TCP sessions to individual queues, and so the likelihood of a multi-queue environment involving data flows to the same destination actually becomes more of a reality with NVMe over TCP, which means that it's not going to be quite so rare after all. So one possible solution is to add more buffers to the problem so that you can avoid the overflow problem and not have to suffer the penalty, or rather, let me rephrase that, will suffer the penalty of extra latency. So there's a trade-off there. But there's another solution here. So one of the solutions that we can do is tell the sender to slow down before the actual drops happen. So now we're looking at a more proactive approach, rather than waiting for the TCP packets to get dropped and the window sizes to reorient themselves. And this is where data center TCP comes in, which we're going to talk about in just a second. And so we're going to be using data center TCP, or we're going to be talking about data center TCP, excuse me, which uses explicit congestion notification to tell the sender to slow down. All right, so what does that actually mean? This is where some of the advances in TCP really come in. And from here, there are two aspects that work hand in hand. And remember, this is just one possible way of addressing the problem. I bring it here because this is probably the more common vendor-neutral approach. But there's others that are going on as well. There's more than just DC-TCP to solve this problem. But this is just an example. Okay, so first, there's the ECN, which is explicit congestion notification. It is a proactive method for notifying the endpoints that use the IP header. And when we talk about IP-based storage, we talk about ECN. So ECN is used to first notify every device in the transit path that's ECN capable, including the sender and the receiver. So when we get congestion somewhere in the path, we're going to set the bits in the IP header to notify congestion. We still let the packets through. We don't drop them. We just inject the proper bits into the diff-served field values. Then that's taken by the receiver, which is going to echo it back to the sender and tell the sender to slow down. So we do that as long as someone in the path is getting the ECN bits. When we echo it back, say, hey, there's congestion, slow down. We make sure that it happens before the congestion starts to drop packets, and that way we don't have to wait for any kind of timeouts. Now, the way that it works at that point is that the marking is set in DC-TCP, or data center TCP, is the algorithm to achieve a high burst tolerance with low latency and high throughput without having to have the maximum amount of buffer size. So we can create pretty shallow buffers. Think of it this way. It's instead of a blunt force instrument where the presence of congestion causes a severe backoff event, we can now react in proportion to the extent of the congestion. And in turn, this has the added benefit of reducing variability in the sending rate. So we can handle bursts in a much more granular manner. The great thing about DC-TCP is it allows you to use shallow buffered switches. And in fact, DC-TCP can deliver the same or better throughput than TCP while using 90% less buffer space with a high burst tolerance and low latency. So what happens if we use DC-TCP with ECN in an NVMe over Fabrics situation with NVMe over TCP? Supposing that we have a sender that is connected to a host with multiple queue pairs, each of them has their own TCP session, notification will get sent back to the sender on a per queue basis. The sender can then understand what's happening and then pull back on the traffic. Whereas before the packets would have been unceremoniously dropped from the sender, and the sender receives the notice via timeout, and that's very expensive in storage terms. Now we have a consistency of the traffic, and it's far closer to what the application expects when using TCP. And poof, Bob's your uncle. So we're heading into the home stretch here, and looks like none too soon with the timing. I know we're going to have a really long Q&A blog on this one. I've thrown a lot of stuff at you, and we probably generate a lot of curiosity about the specifics. And if the questions are any indication, I know we have. So despite how much we've gone over, there are a couple different aspects that we could have also thrown in for good measure, just ran out of time. But let's return to this graphic, which seems so long ago now. We've spent some time with the network at this point, but we can't lose sight of the nature of the relationship between the host and the corresponding storage, which still treats it like memory-like semantics. So we must think of NVMe devices as remote memory, even if it's an imperfect metaphor. Work with me here. So while that simple green arrow represents a connection between the host memory space and the NVMe controller memory space, we've seen that there are a lot of players, to be named later, that can affect just how well it works. We want that arrow to be as short as possible and as reliable as possible and with as little variability as possible. So it becomes important because the reality of the situation in many networks is that there are several green arrows in our data centers. NVMe queuing is dependent upon that communication, but if we happen to mess around with what goes on inside of those green arrows, we can wind up running counter to the goals of well-designed storage networks. And given the potential of how much throughput we're talking about with NVMe and NVMe over Fabrics, the impacts of this can be enormous and can cause enormous headaches for everyone involved. So I think with the summary, we're going to bring it back to Tom now, who's going to wrap things up for us, right?
Actually, I think that I'll take the summary. Just one last slide to this. summarize what we talked about here. So in terms, when you look at NVMe-over fabrics and NVMe over TCP, it's more than just fast storage. I mean, it is fast storage, but it's more to pay attention to when you go ahead and understand the relationship between storage and network. We also must not forget that that each transport has its own methods to basically digest high throughputs and high speeded feeds and handle congestion. If you look at NVMe TCP, it's a high performance, it's ubiquitous, it's well understood, and it's a new NVMe transport that you should go ahead and try it yourselves. If you look at how NVMe TCP works, although running over Ethernet like some of the RDMA flavors, in terms of the command processing flows, it actually looks more like fiber channel in the sense that it uses messages semantics. And it's available now. The standard is ratified and available online. We have both Linux and SPDK as early adopters already supporting NVMe over TCP, which is finding its way to the different Linux distributions, and others are coming as well. And one last thing is that when you understanding that storage and network react with each other, and network is not just an arrow, as Jay mentioned, paying attention to that will sort of dictate and determine how well your solution works end to end. And with that, I'm going to give it back to Tom.
Thank you, Sagi, and once again, thank you very much to our presenters today. I think they did a fantastic job. We've generated a lot of questions, and I'm going to ask one or two of them now, but I'm afraid given our time constraint, we're going to have to carry the bulk of them off until the Q&A blog. But a simple one that I believe Sagi has already addressed, but will kind of addressed, is, let me just find it because my window just moved on me, is that in regards to latency, what do you mean by absolute latency is higher than RDMA by several microseconds? Do you mean less than 10, tens of microseconds, or hundreds of microseconds?
Well, that's a good question. And the answer is that it very much depends. It depends on what implementation you're using. It depends on what sort of infrastructure you're running on, and it depends on the controller implementation, whether it's an open source or commercial. And overall, if you go ahead and download the upstream Linux NVMe TCP, you should see in the orders of 20 microseconds difference tops in terms of latency, but that also very much varies between the workloads. So in the overall answer, I think that if you're interested to understanding the difference, you should try it yourself and see if it works for you.
Yeah, but also don't forget too, this is more of a yes and kind of a thing too. Don't forget that when we are running NVMe over TCP on a traditional or a typical TCP network, it's not the only traffic running. And so the additional latency that exists inside of an NVMe over TCP environment is also going to depend upon what is currently running on a TCP network, how it's currently designed, what kind of throughput and bandwidth allocations you've got, how many switches you're going through, how old the network is, and whether or not you've got various speed mismatches or stub networks. There's more to it than just the canonical latency that goes between a host and a target based upon the protocol. So the design will also have a profound impact as well.
Yes,
yeah,
thank you very much. Okay, Sagi.
Yeah, I was just reiterating that the question is very wide and has multiple different answers, I guess.
Yep. Like I said, it was a yes and. I agree. Everything you said.
So there was a subsequent question to that, was that should we look to implement NVMe TCP on a separate network for a storage network, or can it exist on the existing traffic with the existing traffic on the network? And I'll let either one of you guys address that.
Well, oh, go ahead, Mr. Giddy, if you want to. I heard you take a deep breath.
No, you go ahead, Jay.
Basically, this is going to matter depending upon the mix of traffic workloads that you've got inside of your network. So generally speaking, if you find yourself being starved of traffic on a typical link in your data center, you may want to seriously consider running it over separate links and even maybe on a separate network. It will depend on what your current mix is, what your application audit tells you, what kind of I/O throughput requirements are necessary, what kind of growth pattern you have in your workloads. I think one of the great things about this is instead of thinking about having to do it, you think of it as having an option to do it. Many switch vendors provide the opportunity to segment out your traffic based upon types, and it will also make a difference depending upon what kind of architecture you've got back in your core. But you have the option of doing whatever's necessary to make it work right.
Very good. Well, we've come to the top of the hour, and it's time for us to close down some of this stuff. So as you can see on the presentation, there's a whole bunch of links there for some more information, as well as Jay and Sagi's Twitter handles. So if you have any questions that have not been answered, and unfortunately due to time constraints, there are a bunch of them, we will be answering those in the Q&A blog that will be available within 1 or 2 weeks. When we close down the webinar, you'll be given the opportunity to rate and comment on the webinar. And we do ask that you provide your feedback, because we definitely use this to rate ourselves and to see how well we did and what we can do to do better. Also, we have some upcoming NSF, Network Storage Forums webcasts coming up. The network requirement for hyperconvergence on February 5th. You see the registration link there. And also the scale-out file system architecture overview on February 29th. I've also shared the link to the slides from today. And with that, like I said, please rate this webcast to provide us feedback. This webcast, as well as others, are available from SNIA. And please follow us on SNIA NSF. Thank you very much for attending, and please, once again, fill out the survey because it's very helpful for us. Thanks again.